No, sir, there is some disturbance. I mean, there is disturbance and audio voice is breaking in between.
The voice now audible properly.
Voice is breaking, sir. Voice is not clear. It's breaking.
So actually, your voice is breaking too. I guess your connection is not that good because Sumit is saying that the voice is audible. Just check your connection and let me know. Sumit, is my voice audible properly? Audible. So, Philastia, please check your connection. So I'm sharing my screen.
Hello.
A little bit disturbance is there. Okay. I guess it's the fan sound. I'll take care of that. Hmm. Hello. Is my voice audible now clearly? Sumit. Okay. So we'll proceed. I guess the timing is not allowing everyone to join, but some people said that we should start from 4 and not 6. Then I started from 4. Then people said we should shift to 6. So uh, there is a mismatch of time, but I will start doing stuff here, and all these things will be recorded and posted online. So anyone who want to watch these things, they can later on watch all these things, irrespective of if they are present now or not. So I'll start with the SOAM portal. Mm, Go to. So which question was doubt from assignment
Yes, sir.
5?
Yes, sir. It's question 3.
I guess assignment 5 answer has not been released, right?
No, sir. I just want to clarify that question. Can you go to question number 3? Yeah. Question number 3 is which of the following cost functions are symmetric? A is mean squared error and C is KL divergence loss. Both are regression, and B is I think it is soft margin loss. So how come A and B are symmetric? I didn't get that. Can you hello?
Okay, okay, I see. So, yes, let me read the question. Do the following cost function is following cost function are symmetric. Metric symmetric metric on P and P dash. Consider P equals to target output, P dash equal to predicted output. Give me a minute. Where's my phone?
Sure, sir.
Symmetric attacks, right? But symmetric will be mm, symmetric are those, right, which are metric matrices. But uh, So they're saying they're like symmetric, right? So uh, let's say this p minus p hat. Okay. So this is the equation given, right? Uh, yes. So it's like the two norm, right? So why this is symmetric? Because uh, this will be uh, equal to p hat minus p 2 norm, right? Because so square, actually the square is given, which is like similar, right? P minus p hat square will be equal to p hat minus p square. So by replacing this p and p values, it is coming the same because square is there, and the positive number square will be say, equal to the negative number square. In case of the second part, there is a log, which will be log of 1 plus e to the power minus 1 plus e to the power minus p into p hat. So if I replace p and p hat, that will be equivalent to log 1 plus e to the power minus p hat dot p, which is again the same, right? P hat dot p equal to p into p dot p hat, right? So since like by exchanging the value of p and p dash, the metric remains the same. These both are symmetric metric. But if you go to the third one, p into log p by p dash, here what is happening is that here, like if you replace it, uh, this one is a, this
Understood,
one
sir.
is,
Understood, sir. Yes, sir. What I thought is, sir.
yes, yes,
Yeah, I got it. What I thought is how A and B are both symmetric. I thought, but itself, I didn't thought that itself it was symmetric.
yeah,
Yeah.
like,
Now,
I mean,
the question is itself it was symmetric, right?
yeah. I
Yeah,
mean,
understood. Yeah.
yes,
And sir, can you go to fourth one and about sparse autoencoder? One question was there. Can you scroll it down? Fourth assignment.
okay,
Down, sir, down. Just to go down. Regarding that fifth question, I think, yeah, not fifth question. Sparsity means it makes weights to zero, right?
yes,
It brings the value of weights to zero. So what happens in a sparse autoencoder is it brings the value of weights to zero is also is the correct, no?
yeah. I mean, what the sparse autoencoder do is that it is question number 5. Right? Yeah. So what it does is that it selectively makes the weight 0 to introduce sparsity.
Hmm.
Uh, hmm. So it makes the I mean, yeah, it introduces sparsity.
Yeah.
Uh,
So A is also
A should
correct,
be
no,
the
sir?
answer. Yeah, A should be the answer, I guess.
Then the answer given is
B, right?
B, which is not actually.
It increases the redundancy among the weights.
So it is not the answer, right, sir? How it will because it is making zero. How it will be increases the redundancy by making zero.
Yeah, it is making 0. That is clear, right? But redundancy, like it can be said that okay, if
No, no,
too
no.
many
If we
too
go,
many weights,
sir, yeah, if we go to answer B, by making zero to the weight, how it will increases the redundancy? That one I didn't get. Actually, I was thinking since so long. I mean,
Redundancy
from the
means
day.
that
Yeah.
suppose like you made five weights as zero, so
Hmm.
now all these five weights are same. I mean, we can say that all these five weights are redundant, but that shouldn't be the
Then
answer. It should be the value of weights to zero, I guess.
yeah, what
So
we can say, it is similar to dropout, right? Dropout. Make it in CNN. Dropout is also, it is similar to the dropout. So
yes, yes,
it is not even over there we can't say that it is redundancy. How come it is here redundancy? Here the only regularization technique is changing here and over there. Here making zero is nothing but we are regularizing the neurons.
yes.
So how come it is increasing the redundancy? That
It should
one.
be the option one, I guess.
So it should be the answer. One is the answer. Okay. So one more question, sir. Week one. Can you go to week one? Yeah,
Week one. Okay.
week one assignment.
It's loading. Yes.
Yeah, yeah. So second question. Which
Yeah,
of the
we
following is
discussed that.
structural structure?
It should be like one,
Actually,
right?
it should not be there. There is no option. Actually, the B only three has given. One and
Yeah, yeah.
the given answer is D. I think both one and two. But co-occurrence matrix is not structural, right?
No, it should be like two and three, I guess.
Yeah, there is no option. So these three got wrong for me. Actually, I mean wrong for me in the sense I have given correct, but I have chosen B here, and whatever I have discussed both the questions, I got 0 marks.
Yeah, actually, this was also one problem that we got while discussing in the week
Yeah,
one.
yeah,
Uh, yeah.
yeah. Maybe I
So
was absent on that day. Maybe.
yeah, yeah. So
Yeah.
I guess it's an error for everyone. So I guess the course
No, no,
coordinator
sir.
will.
Those who has given D might be they correct, right? By
Yeah,
mistakenly
might
they
be.
has given. By
Yes, yes.
mistakenly they has given.
They might give grace mark to everyone, but so all these things. So my duty is just to come live and clarify some of the doubts or clarify concepts and assignment doubts, not like for following all these things. So I mean, question answers and exams scheduling. This was done by the other NPTEL team. So you can contact them regarding this
So
if
how
it
can I
is
how can I
incorrect.
contact, sir? There are three questions, right? Now I'm losing marks. So can I? I mean, I can get those 3 marks, right?
I mean, if you contact them and chat with them, like you must have been given some mail address or something to contact the admin.
Okay, 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 sir. Yes. Okay, sir. Thank you.
Thank you.
That.
Okay, so I guess we're done with week three last week. So we'll be starting with week four, and in week four we have stacked autoencoders, denoising autoencoders, and sparse autoencoders. I guess these three type of autoencoder are there in week four. So let's just start.
So can I raise a question in that ask a question forum?
Yes, you can. Okay, so what we're doing is now we're doing MNIST with stacked autoencoders. MNIST and fashion MNIST. So, okay, so this I need to do install. Give me a minute. This will take for some time to install. Okay, so yeah, so we'll run this notebook MNIST with stacked autoencoders. First we'll load the packages. Okay, so then we'll be loading the data. Yeah. So here we're loading the dataset. Like last time I discussed how to load dataset using torchvision.datasets.mnist, and then we're converting it to a train loader. So train loader will be a pointer which will point to the dataset. When we will query the dataset, it will give us like a thousand batch size um, of data, and which you can use further for our task. And we are defining the class in letters. So classes were initially in numbers from 0 to 9. We are just defining it as a word. So we did that. This block is for checking if the GPU is there or not. We did that. And okay, so this is the autoencoder. So as we discussed last time, the autoencoder, so to define any autoencoder, so define any neural network, we need to define a class of the neural network, and it should inherit from this nn module. So this nn module is a class for neural networks, and since we are inheriting this class, we will be getting all the functionality that it holds. So this autoencoder in this autoencoder in the constructor itself, we need to define the encoder and the decoder. So here the encoder is of this F, like 28 plus 28 to 400, and the decoder is just the opposite, as we discussed earlier, 400 to 28 plus 28. And in the forward, what we did is that we passed the input to encoder. We got a encoded sample Z, and that Z is passed to the decoder, and we get a reconstructed sample X hat. I just renamed it so that it will be easier for reading. Okay, and we got the net and we printed the net, and we transferred this our neural network to the device. Like we have to transfer everything to the device. So here the device is GPU. If you have a GPU, you always have to transfer this network to your GPU, and your data set to GPU, such that you can leverage the power of GPU. If you do not transfer it, you won't be able to use, even if the GPU is there. So I'll just print the net. See, this is the net. So I'll just try to write it. So our autoencoder now is, so is the input layer, which is 28 cross 28, and it is getting connected to a hidden layer of size, I guess, 400, and that is again getting reconstructed to a vector of 28 cross 28. I can say that if is an input image, let's say 7, it is 28. 28, it is getting flattened here to this 28 cross 28 length vector, which is equals to 784. And here the operation is called unflatten. Okay. So we got the network now. Then it is for training. Uh, okay, so it is for now. So this is the code for training. We're training the autoencoder. So the number of iteration we set is 10, and the learning rate is 0.98, and the criterion is this MSC loss. So if you recall, in the last class, I told about what are the 4 steps that we need while training a neural network. So we just go to the weak force note. First is the network architecture that we defined earlier. Then the flow of information, like how the information should flow. It should pass to the encoder, and it should be getting decoded. Third thing is the loss. We need to define a loss, or you can say the cost function. Here the cost function is MSE, the mean square error, which is also called the criterion. So it's the mean square error. Then optimize the optimizer. The optimizer is SZD, which is defined earlier, I guess. Yeah, you haven't defined the as optimizer. Yeah, it is sort of doing all these things by itself. It is not defining any optimizer, but it just used the PyTorch function for that. It's fine. So, okay. So what it is doing is that so if iteration equal to 10 means that it will go over the entire data set 10 times. So we're just doing a for loop over the iterations for epoch in ranged iterations. So for data and train loader, so as I told that the train loader is a pointer. This train loader is a pointer to the data set, and each time you iterate over it, it will give you a batch size, a input size of batch size 1000, right? So okay, so data and train loader. What you're doing is that we're taking out inputs and labels. Then we are flattening it. So input dot view minus 128 dot double dot to device is this line is similar doing operation that is similar to this one. This one is flattening 28 to 28. It getting flattened to 784. This line. So after flattening, we're doing the we're just zeroing the gradient. So zero is a gradient. I mean net dot zero grad. So so actually what happens is that in a neural network in PyTorch, when you calculate the gradient, we should zero out the gradient that we calculated earlier. Otherwise, it gets added up. That's why we just zeroed out it. Then it's a forward pass. So if you remember, I also mentioned the steps for it. First will be forward pass, then calculate loss, then backward pass, then update weights and biases. So it's the forward pass. we pass the input through the net and got the output forward pass. Then is loss, calculate the loss. Second step is calculating the loss. You can see here the loss is between input and output, is between like x and x test. And third way is back propagate, backward pass. So here it is loss dot backward. So loss dot backward will flow the gradient backward. And the fourth is update weights and biases. So for to update the weights, or we can say the weights and biases are also called the parameters. To update the parameters, what you are doing is that for all the parameters, we are just so this is just this step. Weight equal to weight minus learning rate time gradient. So we're doing this step here. So and we're just keeping track of the running loss. So I'll just run it, and you can see the autoencoder getting trained. You can see the error is reducing one epoch at a time. The training, why has it stopped? I don't know. Like it should be printing that training has finished. It stopped after fourth iteration. Hmm. Okay, now the training has finished, and we can see that the loss has reduced over time. And yeah, so this is of till this point, it is the normal autoencoder that we ran, and which we ran also earlier, and we saw the reconstruction scores, and we saw the weights in the last class. So so this in this we'll be adding a stacking layer. So what's the stacking layer is that we're adding another two layers in the encoder and decoder sides. So let's just see like how it looks like after adding these layers. So what we're doing is that we're converting this the same architecture to a different like we're adding other stacking to the same like let me in feature and out feature. Yeah, it's like doing the same thing and just adding here. So this will be passed to a $400, then that will be passed to a 256, again passed to a 400. This will be connected. This will be connected here. So now the dimension of hidden is 256. instead of 400 now. So in between we are using tan(h) as a uh, activation function. So this is the new architecture, and let's see by training it over the new architecture. Of course, the architecture is bigger now. All the steps will be same only, nothing new. Okay, the training has been done, and so what is the advantage now? The advantage there is that instead of training this entire thing from scratch, what we did is that we trained this small network, then we stacked other layers on top of these uh, layers. So what happens by this is that we don't need to train the weights that we trained earlier. So initially we will train a weight, we'll train some weights, and that weights will be used again in our next training instead of using all the weights from scratch. So, so there will be some pre-trained weights which will be utilized, and and that will be used for our training instead of doing it from scratch. And so in the last class we saw that how we modify, like how can we modify the autoencoder for classification. We just need to remove the decoder layer, I guess. Yeah, so decoder layer needs to be removed, and instead of decoder layer we need to add a sequencer layer, a fully connected layer, and that will have a softmax, a log softmax activation, and that can be used for our classification. So if I just show you here, what we will do is that so now we have a network that has input size of 784, then is going to 400, and it is going to 256. So this thing is that and 7 is past. So all these weight W1, W2 are now completely trained. So you don't need to train this. So these are completely trained, and so these are the weights and these are the parameters such that such that if you pass the input 7 through this, you'll get an output here such that it can be used to reconstruct the same 7. That means this Z has now very useful features. So you can use it directly to pass it to a 10 layer neuron, which can be used for classification, which will give us the Y, and which can be used for classification. So what they are doing is that they are removing this part, everything out of it, and instead just adding a 10 layer, adding a W3 and a 10 layer neuron here, and this will be this is our Y, right, which will give probability score for the classes that we are trying to predict. So yeah, so this will be the case, and here yeah, here we are having this 7 is getting passed to 10, and we'll use this Y for our loss. So this is the classification architecture. If you see here, the classification architecture, if you see here, like the input layer is 784, then it is getting passed to 400, then this 400 is getting passed to 256, and this 256 is getting passed to 10. I wrote 256, right? Yes. So this is the architecture, and so this is the code for training the classifier. Let's just train the classifier once. and we're printing the test accuracy, you see that the training error should reduce over time and the accuracy of the test set should increase with time. And yeah, you can see the accuracy is increasing and it has touched 90%. And if you train this MNIST dataset from scratch, you have to train for a higher number of epochs to get here, to get 91.71% of accuracy. But here they're saying that with only 10 iterations, you are able to get the accuracy. Let me run it again to gain some more accuracy. Go till 95. Let's see if it is giving 95 or less than that. Okay. So it's 93.84, which is not bad. So we'll stop here and see if this is something. Okay. But I guess see 93.84 is still a good accuracy. So then performance of different classes. So just run it. So this is giving like suppose like there are 100 images of class 0. How many of it has been correctly detected and how many of it has not? So in case of 0, 97% of the input has been correctly detected. In case of 1, same 97. The lowest I guess is for 5, it is 90%, and for 9, it is also 90%. So it's just a study, it doesn't matter. So this ends the stack.encoder. I also described it in the um, notebook itself. And so this is the same thing with fashion MNIST. So as we as we did last time, we did for MNIST and fashion MNIST. You can run it on your own. I will also try to run it on my side. I'll not spend much time on it because it's just the same thing. The same dataset size is same. Instead of numbers, it has now dress and shoes. Okay. We're loading packages. Then we're loading data. Loading the available of GPU. Everything here will be same. The network, training the autoencoder. So what happened? High progress is not found. Hmm. Yes, I'm not able to run this notebook. There is some error with this progress bar that it is trying to print. But I guess if you run from your side, it will be just fine. Let me try this. It is not. It doesn't have option for me to install in this SSH. Uh, Let me like stop running this. It will be very much similar to the first one, but this TQDM is creating the problem. What you can do is that we can replace this TQDM with a normal progress. For that time, $10. Started running here also. Then we stack the layers and then we train again. Here the error stopped at 0.06 and started from 0.1, but here now the error has started from 0.8, and now the error will go low below this 0.06 because we used the previously trained weights and made progress on it. So that's a yeah, we can see that the error that we have reached now is 0.04 instead of 0.06, which we reached with the normal autoencoder. Then we modified for classification, and here also I need to remove this one, the train data loader, and yes, now we'll train for the classification. We saw that the accuracy that we got is 80%, which might not be that great. Let me run it again. Okay, so we got, so there is not much of an improvement. It is going till 83, I guess. So we'll have to settle with that. Give me 1 second. I need to give the link for the video in the mail. Sorry. So here is all the videos that is residing. You can go to uh, this channel and find all the previous recording. I'll just post the last YouTube sessions live videos, live session YouTube videos. So yeah, week 4 is live now. This is going on week 5. Okay. So we trained the classifier and got around 82.5% of accuracy. So yeah, so this is done, I guess. Then we can go to SPATS autoencoder for MNIST classification, and then denoising autoencoder for MNIST classification. Then we will be done. Yes. Okay. Okay. So before starting SPATS autoencoders, do you guys have any doubts or anything that need to be discussed till week 5? Like any concept doubt, conceptual, or any questions from the assignment, you can ping me or you can push in the chat. Uh, so I'll be starting with Spark Short Encoders. So since all the concepts are clarified in the class itself, I'll just going through the codes and reiterate the same thing in case you haven't understood it completely. So this will so we will complete week 4 today, and we'll cover some part of week 5, and we are lagging behind 1 week, so I'll try to cover that. And the next class I will clarify all the doubts from of assignments of week 3, 4, and 5. So in the next class we'll complete everything till week 6. So after that we'll not be discussing any other thing that is there in the week 6 till week 6. So but currently till week 4, if you have any doubt regarding autoencoder, ask me, because after week 4 there will not be anything regarding autoencoder. And in the week 5 we have all the things that is related to deep learning, so we'll discuss that. So yeah, so before that, like, let's just take a 5 to 10 minutes, 5 minutes of break, because like I've been talking since 1 hour, so I need a break. So you guys can like ask questions here, or just let me know which notebook that you ran, and you got any errors or something, or you want to understand any specific part of the notebook. Meanwhile, okay, I'm going on mute. Okay, so yes, we took a 10 minutes break. Uh, where were we? Uh, okay, so let's just run this lecture 19 notebook and which is on sparse autoencoder for MNIST classification. The code will be similar, but uh, there will be some difference. So I will discuss them. Mhm. We're importing the packages. We are loading the data sets and checking if GPU is not GPU is available or not. Defining the sparse autoencoder. Okay, so we're defining now the sparse autoencoder, which is similar to the later one, 28 cross 28 uh, to 400, then again 400 to 28 cross 28 cross 28. This is done, and here we are keeping the weights of encoder and decoder for our future analysis. So here we will um, so remember we defined the 4 steps that we need to do while training any deep learning model. First will be forward passes, second will be the loss calculation, the third will be back propagation, and fourth will be updating the weights. Now in the last step, we need to add a sparsity factor, and here the sparsity factor is 0.1. So what it does is that while we are so I'll just define it here in the this session. So given a autoencoder, okay, let's just topic mark it as sparse autoencoder. Sparse autoencoder, okay. So given autoencoder, this is my Z, this is the reconstruction, X and XZ. The typical loss is, so this is the encoder and this is the decoder. The typical loss is MSA between X and XZ. This is the loss autoencoder, loss AE. But in case of sparse autoencoder, what we do is that we want this MSC to be low, as well as we want the norm. We want the norm of weights to also go down. So, so what we're doing is that we're taking the norm here. Here we are taking the norm of the encoder weights, the like torch dot norm net dot encoder 0 dot weights. So we'll take the encoder weight encoder. I just put it here, weight encoder and weight decoder. So we took the weight encoder norm to norm, and then we are multiplying it with the sparsity factor. So how much we want to make this weight sparse. So there's the sparsity factor of 0.1. We're multiplying that, and this is our loss sparsity. So now the loss of autoencoder equals to, so this was our let me rephrase it. This was our loss MSC. So loss of autoencoder will now be loss of MSC plus loss of sparsity, which will be equivalent to
x minus x hat square root plus 0.1 times encoder weights LP naught. So this is this is the thing. So the same thing we sort of created here. We um, multiplied a lambda to we multiplied the sparsity factor to the norm of the weight, and we defined the total loss as the loss, I mean the MAC loss, and the L1 norm loss. And so this is only the change. If you go back and see, this is the only change that is there between these two codes. And also we are evaluating as every time uh, we are 1 second. Also we are evaluating every time we are reaching some stage. So and we're the iteration is 20, and also we're evaluating after some period of training. So let me train this network first and see how it is performing over time. Multiprocessing data loader has no attribute next. Data iter next. The mean square error should be reducing with time. Let's see how it is responding. Okay, the training has been done. So let me see like how the reconstruction has performed. As you can see, the reconstruction is not that much great. Okay, this is the weight visualization and decoder weight visualization. But I don't know why they put this thing, since the reconstruction is not that great, I would say. Okay, let's just try the accuracy. Maybe that next variable should not be changed, but I changed it anyhow. We'll see like why the reconstruction is not that great. If you could remember last class, the reconstruction was good, but I don't know why the reconstruction is not good now. So this is like normal, the performance of classification is good, but I'm not sure why the reconstruction is so bad here. Let me turn it again and see if it increases. Okay, so it is now giving error. Let me let me increase the iterations now and see. Let me make it 100. Let's see what happens now. I have to wait a bit, but I guess we can see if it is working or not. Maybe there is some bug in the code that they provided. Okay, the training has been finished. Let's see how it looks like. I guess there is no improvement. Maybe this notebook is not that good. They haven't fine-tuned it properly. Anyway, let's move to the next notebook. So I'll briefly discuss about what is denoising autoencoder, and then we'll go to the code of it. Denoising autoencoder. So first thing is that the autoencoder in the vanilla state has this property that given a image, input image or an input data, it will take it, it will encode it to some latent dimension z, then it will decode it back to 7. Okay, but the beauty of a denoising autoencoder is that instead of giving clean 7, if I provide a very noisy 7 or any noisy image with these noises, Gaussian noise or any sort of noises added to it, if like you have a very old image or something, then this if the autoencoder is denoising autoencoder, it will take this, it will map it to a latent variable say. Then while decoding, instead of giving you noisy levels, it will give you clean 7. Okay. So this is the use case, right? So you might be thinking like, where should we get this noisy images? This shouldn't be this noisy. Like there can be cases where you have a patch in the images, like you must have missing this part of image, or there might be like half of the image is missing, or you are just filling it with black noise, or suppose you have a image and it is very old, and that's why you have cracks and all in the images. So if the image condition is like this, and if you have a denoising autoencoder, you can easily get back your clear image back in the output. So how to train it then? So for training, you need these noisy images. So but we don't have noisy images in the MNIST, right? So what should we do? So first we need to take a image of 7 and add some Gaussian noise of zero mean, and so this is the notation for standard normal distribution or the standard Gaussian distribution with zero mean and variance of 1. We take that and we added the noise to it. We get noisy samples. So this will be my X, and my Y will be the corresponding 7, but with clear. Similarly, I will do for 3, 2, 1, everything. And now we'll get this 7 noisy images and corresponding this images. And so how to train this? So initially this noisy 7 will be passed to the encoder. And we'll get a Z out of it. From the Z, we'll pass that Z to decoder, and we'll get a initially we'll get some random noise. So so this will be X hat, this will be X. And while doing the mean square loss, earlier we used to take mean square loss between X and X hat, but now we'll take, so this is X, so let's just rename it. So this is X, and this is noisy X. Noisy X is let's say X subscript N, and this is noisy X dash, so X and X cap N. So this is earlier it was N, now, but we'll take the difference between this and this. We want this xn to be similar to x, not xn. Sorry, we want this xn hat to be similar to x, not xn. So that's where we will put it as xn hat minus x. See, like, so as I told, whatever you want to do, like whatever you want to minimize, whatever you want to, you want your end goal to be, you want that to be minimized, right? So you want the distance between this noisy reconstruction of 7 and clear reconstruction of the 7 to be minimized. So that's why in the loss function, you have to put uh, this. So you want to this distance as the loss, such that when it will be minimized, the distance between the noisy 7 and the actual 7 will be minimized, and you will get a clear 7 at the end. So after training has been done, after a few iterations, when you will pass a noisy 7 in the autoencoder, you will get a clear 7 as the output. So this is the basic idea. The loss is now just loss A just equals to xn cap minus x. It's not MSC, mean square distance. Nothing fancy is going on. So I'll just run this notebook. I guess this will be the last notebook that we'll be running today. So it will complete everything till week 4. Yes. And yeah, so we're running this, loading data. All these things will be same. No need to worry. Defining the autoencoder. See, in the defining the autoencoder, there will not be any difference, because as you can remember, so the autoencoder architecture, in the autoencoder architecture itself, there is nothing that is there like the difference. But the only difference that is lies is in the loss part. So the autoencoder will be as it is. I'll just define and print it. You can just do 784, 400, 400, 784. While training the autoencoder, we first need to add, okay, so this step is there. We need to add a noise of 0 mean and unit variance, or you can set as you wish. So this is the number of iteration that we defined earlier. Learning rate we defined already earlier, like what is learning rate. Noise mean, so here the mean is 0.1 and the standard deviation is 0.2. So here it will be 0.1, 0.1, standard deviation is 0.2, and the lambda. So also we are also using sparsity here. Sparsity is 0.1. The criterion, the loss is MAC loss, and the optimizer is Adam. Adam is one type of SGD. So we'll learn about all this optimizer in the week 5. If you have seen that, you must have learned. So see, so we're iterating over all the iterations, and we're iterating over all the data loader. We're getting inputs and labels. So since the batch size is 1000, we'll be getting 1000 images and 1000 labels. So this is the ideal output. So see, here is the ideal outputs. Inputs is there. We're just flattening it, and we're getting the ideal output. And this is the noise. Ideal output dot data dot new. So we're taking this safe, and we're sampling from a normal distribution. So the noise, so I'll just tell how the noise is getting sampled. So what we did is that, so we took the dimension of this. The dimension will be 784, right? So we are defining a 784 dimensional Gaussian distribution. Gaussian distribution. Two-dimensional Gaussian is like this. And since the mean is 0.1, this will be 0.1, and the variance is 0.2. Okay. So what we're doing is we're defining so this is two-dimensional. Similarly, we're defining a 784 dimensional Gaussian, and we're sampling points from it. So each time we sample, it will be picked from different points, and we will get a noise of dimension 784. And we're directly adding that noise to the input. Like you would take this 7 plus noise, you'll get a noisy 7 from it. So here the ideal input, and here is the noise. Noise we are sampling from normal distribution with noise bin and noise standard deviation. Then we are adding the ideal outputs, the ideal 7 without the noise 7, then noise. adding this, and we're getting the inputs. So this is my XP, sorry, XN. So ideal output is the X, and XN is the inputs which has noise, XN. The rest is them. We're just doing the zero grad, and then we're forward passing, then we're calculating the loss. See, the loss is now calculated between outputs. Outputs is now is xn hat, not x hat, it's xn hat. And we're calculating the output between xn hat and x. Since I mentioned the x is ideal output and inputs is, I'll just write ideal outputs equal to x. X ideal output is equal to x, and inputs equals to x subscript n, right? So we need the difference, the loss between xn hat and x. So outputs equals to xn hat. Outputs equals to x subscript n superscript xn hat. So x hat n, I can say. So since we need the difference between xn hat and x, so here will be the loss will be between outputs, which is xn hat, and the ideal outputs, which is x, right? So this is the loss. And since it is a sparse autoencoder, we are adding lambda to it and getting the L1 norm, and the total loss is now loss plus L1 norm. The similarly that we discussed earlier here in the sparse autoencoder here. And we are back propagating the loss now, and we are taking a step, and then we're tracking the loss for each iteration. Let's just train it for 20 epochs, as it said earlier initially, and we can tune it according to our need. Now the training has been done. Let's see how the autoencoder has performed. It must have given visualization for, okay, no attribute next. The 710. What happened now? Okay. Next by this. This is not performing well. I don't know why, but the output should be like the clear 7. But here it is not giving me any good outputs. What I will do is that I will create notebooks by myself, and I will try to do the same thing in the next lesson, so that how the denoising autoencoder is working, because I'm not sure why it is not working. Let me just comment these lines and just do the normal loss and see. Let me try once again. Yeah. See, so actually, I guess that scarcity part was not that well implemented. See, now this is the noisy in 7, and this is a denoised output 7. You can see that the input is this noisy one, and the output is clear 7. We'll visualize these weights, and okay, you can see the weight, the initial random weights and the trend weights, and it has some pattern. And similarly, you can visualize the decoder weight, and we can modify the autoencoder for classification. But I guess this is the same thing that they're doing, just attaching a new layer on top of that. Let me just train it and see. Okay, we got a accuracy of 92.3, and I guess the class level performance will be good. So yeah, so sparsity, like removing the sparsity thing, it's really working. What I will do is that I will just increase the noise now. Instead of doing just 0.1 and standard deviation of 0.2, let's just put mean as 0 and standard deviation of 1. In this way, the noise will be more. Let's just see how it is doing with this kind of noise. And we will then close the session for today. So earlier the noise was 0.1 and 0.2. The mean was 0.1, the standard deviation was 0.2, but now it is 1 and 0. Mean is 0 and standard deviation is 1. Let's see how the noise is getting handled here. And if it is too much of noise, this might not able to handle, I know, but let's see how it is doing. Okay, the training has been finished. Let's see where is able to. Okay, so I guess like the noise here is too much, like it's almost noisy, but still it is able to recover the 7 out of it. See, you can see clearly the 7, I guess. Yeah, so I guess with mean 0 and 1, it is too much of noise. Let's not go there that way. But with mean of 0.1 and the standard deviation of 0.2, it is able to retrieve the image as it is. So I guess this ends our today's session. I'll stop recording. If you have any more doubt, you can ask in the doubt section, and go to the YouTube video channel where you can find all the videos that has been done till now, and I'll be uploading them to there. Okay, so thank you. Bye bye. Good day for today.